Hello everyone. In today's class, we are going to learn rate of loss of heat and rate of cooling. Rate of loss of heat. I'm denoting with RH. That is what rate of loss of heat and rate of cooling. This one I'm denoting with RC. Okay. So rate of loss of heat and rate of loss of cooling. These two things we are going to learn in today's class. Okay. So let's start first one, that is rate of loss of rate of loss of heat in bracket denoted by RH. Okay, let's start. Now, what do you understand from this rate of loss of heat? What do you understand from this rate of loss of heat? From this sentence, we can say means at what rate the heat is losing any body. If any body is losing in some proportion, or what you can say with some fraction heat, that is what rate of loss of heat. Okay, or with what rate any body is losing heat, that is what rate of loss of heat. Okay, now see here, if a body if a body at a temperature theta temperature theta is placed in environment of temperature theta naught, then heat loss and what we have to assume here, theta is greater than theta naught. Okay, theta should be greater than theta naught, means surrounding temperature should be less, environmental temperature should be less than the body temperature. Then heat loss by radiation, delta Q is equal to Q emission minus Q absorbed, that is heat emitted minus heat absorbed. Okay, that is equal to how much? A epsilon sigma theta power 4 minus theta naught power 4. This is what? Temperature. Understand? And into what I can take? I am taking T. Okay, this is what? Heat loss delta Q. AE sigma theta power 4 minus theta naught power 4. Now, see here, if I want rate of loss of heat, rate of loss of heat, that is, this is what? Delta Q. So I am writing here dq, and this T I am taking here as a dt, that is what? Rate of loss of heat is equal to A epsilon sigma theta power 4 minus theta naught power 4. This is what? From, you can say, Stephen's law, radiant power. Yesterday we have learned this formula. Yes. So here it is, rate of loss of heat is what? A epsilon sigma theta power 4 minus theta naught power 4. You can denote here theta as a T also or T naught also. Choice is yours. Okay. Right. So this is what? Rate of loss of heat formula we got. Next. Point number 1. Here, point number 1. If two bodies are made of same material, if two bodies are made of same material, have same surface finish, have same surface finish, and are at the same initial temperature, then dq by dt is proportional to area, and therefore I am writing here RH. Okay, wait. This rate of loss of heat is, you have written, no? Wait. I will denote with one letter, that is rate of loss of heat, that is equal to RH is equal to this dq by dt, and therefore rate of loss of heat for one divided by rate of loss of heat for second is equal to A1 by A2. Direct formula you will use, that is in terms of surface area. When we have to use this, when material is same, okay, same surface area, same surface finish, and are at the same initial temperature. So they are at same initial temperature. Then you can write down this. Okay. So note down this. I am giving after that one table also, so that you will understand more. First try to understand this part, rate of loss of heat. dq by dt is a epsilon sigma theta power 4 minus theta naught power 4. Theta is what? The temperature of body. Theta naught is what? Temperature of surrounding or environment. Note down this. Okay, next. Now, second one I am taking, that is rate of cooling. Second one is what? First one we have seen rate of loss of heat. Now second one is rate of cooling. Rate of cooling. And this is denoted by RC. So let's see how it is. Means how, with what rate body is going to cool. Now, if m is the mass of body and S is specific heat capacity, then what we are having, Q is equal to formula ms delta theta. Ms delta theta. And here, if I am taking this dq by dt, what I am getting? Ms d theta divided by dt. Yes or not? dq by dt is equal to what? Ms d theta by dt. Yes, because here it is dq. So if I am taking dq, I should take ms d theta. Now, rate of cooling is what? Rate of cooling, that is RC, is equal to d theta by dt, which is equal to dq by dt divided by this ms. Yes or not? Yes. If you want, you can take one step here also. Choice is yours. Yeah, this is, that implies d theta by dt is equal to, this ms will go here, and that is what dq by dt divided by m into s, that is mass into specific heat capacity. Clear? And now dq by dt value we know, so therefore RC is equal to, in first only we have learned this, you can see here this value, yes, in the first slide. So can I substitute at the place of this dq by dt? See here, yes, I can substitute. So therefore, what I am getting, A epsilon sigma into theta power 4 minus theta naught power 4 divided by m into s. M into s. And if now one more I am adding, that rho is equal to mass by volume, and therefore m is equal to rho into v, then I am getting formula like this. So I'm getting RC is equal to A epsilon sigma theta power 4 minus theta naught power 4 divided by how much you are getting V rho S है ना, rho V S, rho V, and this is specific heat. Clear? So this is what the rate of cooling formula. Understood? Note down. Okay, let's move ahead. Now next. Now for two bodies of same material under identical environments, we can write down below that. This is like note point. How we have denoted that is the heat of loss or rate of loss of heat is dial proportional to ANO. Same like here also. For two bodies of the same material under identical environment. Identical environment means obviously same temperature, same surrounding temperature. Identical environment. The ratio of their rate of cooling RC1 divided by RC2 is equal to A1 by A2 into P2 by P1. Okay. So here I am writing note points, that is dependence of rate of cooling. Dependence of rate of cooling. On what factor rate of cooling is depend? Let's see. First one. Nature of radiating surface. Nature of radiating surface. So what you can say? Greater emissivity. If that material has greater emissivity, faster will be the cooling. याद रखो, theoretical questions you may get. Second point, area of radiating surface. Area of radiating surface. So that is, you can say direct proportional. More will be the rate, more will be the area. Yes. Third one, mass of radiating body. mass of radiating body. That is R is inverse proportional to M. It means what? If R increases or if mass decreases, radiation or rate of cooling increases. Here also what is this? R is directly proportional to area. Fourth one. Specific heat of radiating body. Specific heat of radiating body. So R is rate of cooling, RC. RC. Here also RC. RC. Rate of cooling is inverse proportional to specific heat. More the specific heat, less will be the rate of cooling. That's why water is taking so much time to cool as compared with soil. Why? Because specific heat of water is more. Okay, rate of cooling is inverse proportional to specific heat. Next point, temperature of radiating body. Temperature of radiating body. So RC is directly proportional to temperature, that is theta of the body. And temperature of surrounding, greater will be the temperature, RC will be slow, or you write like this if you want. This one, greater the temperature, greater theta naught, slower cooling. Okay, these are the some factors or dependence of this rate of cooling. You can take your own examples and justify this, all the what you can say dependence of rate of cooling. Okay, yes, note down. Next, I am giving you one table. You can also make like that. Make like this table. Okay, this table is very important. You can write heading like this. comparison of RH and RC and how they are dependent. On this you will get problems. So when this table is with you, you can solve easily and fast also. Clear? So let's see this table. First, in first column you write body, in second column condition, rate of heat loss, that is direct you write RH, and here you write RC. RC is equal to what type? d theta by dt, and here it is what? dq by dt. Enough. Rate of heat loss, rate of cooling. RH means what? Rate of heat loss, rate of cooling. Shall I write here? Rate of heat loss. Rate of heat loss. And here it is what? Rate of cooling. Okay. Let's start. Body is, suppose what? First one I am taking two solid spheres. What I am taking? I am taking first two solid spheres. If I am having two solid sphere, then condition क्या है देखो इसके लिए. If suppose theta comma theta naught comma specific heat comma rho are same. What is that? These many things are same. That is theta, theta naught, specific heat and density are same. Then RH is direct proportional to area and it is direct proportional to radius of the square of the radius of the sphere. Why? Because you know area is equal to what? 4 pi r square, surface area if we will take. And therefore RH1 divided by RH2, RH1 by RH2 is equal to what you will get? Very simple, R1 square by R2 square. Next, in this rate of cooling के लिए what you will get? RC is direct proportional to area and inverse proportional to volume. So it is direct proportional to what you will get? What? Tell me. R square by R cube, and that is inversely proportional to 1 by R. So direct if you want RC1 by RC2, in this case, how you will get? RC1 divided by RC2 is equal to R2 by R1 you will get. Understand? Keep it in mind. Clear? Okay. Let's move ahead. Next point. This is the first one. Let's move ahead. Now second condition, what I am taking. Second condition. Two solid sphere of different material. Two solid spheres of different material. So material is not same here. Okay. Two solid spheres of different material. And condition is what here I am taking, that theta comma theta naught are same. Means here what? Body temperature and surrounding temperature is same. Then what you are getting here, now I am only writing the thing, so remaining you can write rate of heat loss is directly proportional to A and directly proportional to R square, same like previous one. Okay. And here rate of cooling, in this case rate of cooling is directly proportional to area by phi rho C and rho S. Okay, not C. S is specific heat because we have denoted yes, and it is directly proportional to 1 by R rho S. Why? Because here A is there, no? Listen, here A is R square, B is R cube. So R square and R cube, one will get cancelled. It will be here R only. And this is 4 pi R square, this is R cube. Same like here, how it is happening? Same like that. You can see here, same thing it is coming. Area by volume is there, no? So at the place of this area by volume, R square by R cube, and therefore you are getting 1 by R, and that's why I have replaced this. Clear? Good. Let's move ahead. Next one. Next one. Now, different shape bodies like cube, sphere, plate. Different shape bodies different shape bodies like cube or sphere plate. And here condition is what? See, here also theta comma theta naught comma specific heat and rho are same. Then here RH is directly proportional to area, and you keep it in mind, A maximum will be for plate. Maximum will be for plate and minimum will be for sphere. Area minimum will be for sphere. Okay. In this case, as we have learned already, A by V, same you will get. That is rate of cooling is directly proportional to area and inverse proportional to volume. So from this you can find out these all things, right? Next. Last one. Bodies of different materials. bodies of different materials. If bodies are of different material, and what is the condition you can see here? I am taking body temperature, surrounding temperature, then mass and area are same, are same. Then in this case, rate of heat loss is same for all bodies. RH is same for all bodies. And here rate of cooling is inversely proportional to specific heat. You have to think about the specific heat. The one whose specific heat is more, its rate of cooling will be less, and the one whose specific heat is less, its rate of cooling will be more. For example, sand and water. Water is having more specific heat, that's why rate of cooling is less. Sand has less specific heat, that's why rate of cooling is more. Understand? That's why sea bridges and land bridges concept. Understood? So note down this table carefully. Okay. Note down fast. Note down. Okay, finished. One problem I will tell what type of nature you are getting. Let's see the problem. What type of nature of the problem you are getting. So see here, you have to solve. I will give just hint. Try to do yourself. Two spheres made of same material. Two spheres made of same material. Made of same material. Have their radii in the ratio 1:3. 1:3. They are heated. They are heated to the same temperature they are heated to the same temperature and kept in the same surroundings. And kept in the same surroundings at a moderate temperature. Find their rate of cooling. find the ratio of their rate of cooling and the ratio of their rate of cooling. Okay, so let's see how to solve this problem. So what is given here first? What is given? You can see given is what in this problem. Let's see. Given have their radii, same material is there, so same material means rho is same, that is rho 1 is equal to rho 2 is equal to rho 1. Then next they have given same ratio है ना, ratio दिया है radius का r1 as to r2 is equal to 1 as to 3. Heated to the same temperature means theta is same, also theta naught. So I am writing in one line only, direct I am writing, that is like this: rho comma theta naught are same. Okay, and you have to find the ratio of their cooling, that is RC1 divided by RC2 is equal to question mark. Let's go back to our table. You see here specific heat and all will be same. Then how it will be? What type of shapes? Solid spheres are there. Check in the table. 2 spheres are there, है ना? Yes, 2 spheres are there. So how they are? Rate of cooling. यहाँ पे देखो ये वाला 2 solid spheres, last corner, it is inverse proportional to R. Yes or not? So therefore RC is inversely proportional to R, and therefore RC1 by RC2, the rate of cooling is equal to R2 by R1. That is equal to what you are getting? 3 as to 1. And therefore what is our answer you will get? You can write down here, it is very easy. What is that? Therefore rate of cooling for first sphere divided by rate of cooling for second sphere is equal to 3 by 1. Yes or not? Clear? How much easy problem? See, once you know the relation and these formulas, you can solve easily. Although it looks very big problem, but they are very easy. Okay, so try to solve some more problems if you have. Okay, right, so let's stop here, and again we will see the remaining part on tomorrow. Okay, and don't bother about the marks, whatever you got, don't worry, don't take tension. Okay, enjoy the day and bye for today.